Okay, here's a question that arose, and we couldn't locate the question, and the person who asked it couldn't quite rephrase it, so I'm not sure what the question was asking. But by the time I got done with all this, I think the question had been answered, and so did the person that asked it. So let's look at the situation. Okay, the situation was something about a mapping from R6 to R5, but I chose to simplify the arithmetic and just go R3 to R2, which in principle is no real different than going R6 to R5. It's just that you have smaller matrices for this one. So a mapping from R3 to R2 could be defined by the matrix that you see here. Okay, it's a 2 by 3 matrix. And you see that this goes from R3 to R2 because this matrix is going to multiply vectors with 3 components. Okay, so it multiplies vectors in R3. And when you get done, you're going to get 2 rows over here, and of course just 2 numbers in a column. So this is going to be in R2. And the multiplication comes out the way you see it. You just have, here you have 3x1 plus 2x2 plus 4x3. Might not be able to read all that, I got scratched up there. And 5, negative 1, 3, 5 times x1 minus x2 plus 3x3 right there. And we also noted, because I didn't know, exactly what I was trying to explain because we didn't have the question, but I observed that this can be written as x1 times the vector 3, 5 plus x2 times the vector 2, negative 1 plus x3 times the vector 4, 3. If you multiply these out and add them up, you'll see exactly why I said that. The range of the vector space then is the set of sums of multiples of these 3 vectors that are listed here, because of course x1, x2, and x3 could be any numbers, so that these could be any, so this sum could be any sum of multiples of the 3 vectors. Which means, of course, that the sum of multiples of these 3 vectors is the span of the 3 vectors. Well, these 3 vectors are in R2, and the first and second one are not parallel, so we can see right away that this set spans R2. Now, there are other ways to determine that. Just the fact that the rank of this matrix is 2, which is easy to determine. Just doing row reduction. Guarantees that. You need to put these, we're at the stage where we're trying to put these concepts together. Okay, so these vectors are not linearly independent, but they're reducible to a linearly independent set, as any set of vectors is. Do a Gram-Schmidt process on them, and some of them might disappear. A Gram-Schmidt process here would give you an orthonormal basis, but it's unnecessary because, as we just observed, all these vectors are in R2 and they span R2 since any 2 of them are not parallel to one another. Okay, so clearly the set spans R2, so the range is all of R2 with a standard basis. Well, we could kind of sketch the transformation in the usual way. So we have our transformation, which I could have labeled. I get a hold of that chalk. The transformation is T. Now, at the stage when I first drew this, I didn't have the rest of this, the kernel going to the 0 vector, but we then figured out what the kernel is and checked my arithmetic, but the process is as I described it. Okay, the rank of the matrix is 2, and I assume we know how to find the rank of a matrix. That's the rank of the transformation. And the dimension of the domain is 3, so the nullity has to be 1. Okay? Dimension of the domain is 3, and the rank is 2, and it follows then that the nullity is 1. I took this as implicit because I think everybody understood it when I said it, but it's worth saying. The nullity is the dimension of the kernel. The kernel is found by solving this equation. In other words, finding the vectors that map onto the zero vector. Okay, now we know that the nullity is 1, so there's just going to be it's going to be a one-dimensional subspace, which means all the vectors in the kernel are going to be multiples of some vector in the kernel. Any vector in the kernel is all the multiples of that vector. So to solve this equation, we're just going to reduce this matrix. So if I've reduced it correctly, it can come down to this. A quick explanation of my steps. I multiplied first matrix by 5 and subtracted it from 3. I multiplied the first row by 5, subtracted it from 3 times the second row so that the first coordinate would go away, and I got this. You can check my arithmetic. It's not particularly important because we didn't really use it for anything. And then I multiplied the second row by 2 and the first row by 9 and the second row by -2 and added the results and replaced the first row to get this. And that matrix is reduced as far as it can go. Now I could have divided through by the 27 on the first row and the 9 here and gotten 1s here, but this is sufficient because this matrix indicates that 27 times x1 plus 14 times x3 has to be 0, and this indicates that 9x2 plus 11x3 has to be 0 in order for the matrix product to give us the 0 vector. Okay, well then we have free variables. x3, let's take x3 as our free variable, and let x3 equal t. Then 27x1 plus 14t equals 0, and 9x2 plus 11t equals 0. So x1 is negative 14 27ths t, and x2 is negative 11 9ths t. Follows the kernel consists of vectors negative 14 27ths t, negative 11 9ths t, t, or t times negative 14 27ths, negative 11 9ths 1. So the kernel is the span of this single vector, meaning it's a set of all multiples of this vector. We could equally say it's the span of a vector that's 27 times this vector, or any number times this vector. I chose 27 because if I use 27, if I take a multiple 27 times this vector, I'm going to get all integers. And that's easier to look at than fractions. Okay, so multiply all these by 27, I get negative 14, 30, negative 33, 27, and your kernel is the span of this vector. The dimension of the range is the dimension of R2, which is 2, as we saw over here, because these vectors here span R2, and combinations of these vectors that are the range of the transformation. Dimension of the kernel is 1 because of the relationship between dimension of the space, the rank, and the nullity. And the rank is 2, which follows from the dimension of the space and the nullity, which we just found, or the nullity, the dimension of the kernel, which we just found, and everything ties together. Now, individual that asked the question said that was very helpful. Maybe it's just being nice, but that's not necessary. I think the person knows that. So hopefully at this stage of the course, this serves to tie together a bunch of different ideas and help give us a better picture of the vector space. And as we're going to see in the next segment, the eigenvalue and eigenvector picture can be very, very helpful. And where we're headed is we're headed down the road with these ideas, and then with the ideas of eigenvectors, and ultimately get to diagonalization and defining functions of matrices and so forth.